So hopefully people don't have issues loading the object here, because it's already with everything that's run. So we don't have to wait 5 or 10 minutes for everything to be finished. But yeah, so this part is basically the same, because again, from now on, every time we do anything CTMM related, there's going to be a lot of steps that are very similar, like the variogram checking and model selection. So it's very similar to what Chris was already going through. I think the main difference here, I'm just going to quickly run through this, is this part here. Chris was talking about this color function that can help color in different ways. So one of the ways we can do it, besides by individual, is do it by time if already are at the essentially one data set here. So what it does is basically go from red to blue in terms of time. I'm actually going to make the points a little bit bigger here as well. OK. So the main thing here is that visually you can start looking at almost the range residency assumption a little bit. Because if you see like there's a lot of points in blue here, and then there's lots of points of red here, that's a shift, right? And it probably starts indicating that there's something there to be aware of. But if the points, the reds and the blue are kind of all in the same place, that's already a good indication that we are looking at a range residency species. But, yeah, but just a quick way of getting a visual idea of that. So this individual, Pepper from the African buffalo data set, you'll also see here, this is essentially the sampling intervals, right, for all the different locations that we have. I'm actually going to make it bigger. Yeah, so all the different sampling intervals for all the different locations. And we can already see something that's happening here, right? So there was a shift between 1 hour sampling to 2 hour sampling at some point. This was not on purpose. It was just a malfunction of the device. So it kind of shifted between these. So it's also, this is another diagnostic plot. You can use this DT dot plot to kind of visualize and see if there's potentially issues with sampling interval. And we'll see a little bit later in the code how we can deal with this, right? OK, so this is doing the same part of just looking at the variogram. It's not showing the confidence intervals very well in the screen, but you should be able to see it well in your screens, because it's on mine as well. Just a little bit of a difference here. But yeah, so it's essentially kind of the same idea of stabilizing at a certain point. Obviously, there's some fluctuation around a value here, but we can pretty much follow the range residency assumptions. And this plot is just plotting this part here, just zooming in. And we can see that slightly upwards curve indicating that there's some velocity autocorrelation there. But yeah, for this individual, we have range residency, so we can move right along. OK, so if you remember at one point, I was talking about maximum likelihood and residual maximum likelihoods. Essentially, the different ways these parameters are getting estimated, right? And this is a argument you can set in ctmm.select. So if you want to do maximum likelihood, because it's not the default is a different one that I'll discuss a little bit later. But the maximum likelihood you'd have to select here as the argument. And it's a little bit faster than some of the other ones. But obviously, it does come, as you saw, with potential issues if you have low effective or low absolute sample sizes. So it's just something that if you already can guarantee that your data does not require the other methods, maybe this one will speed it up a little bit and make it faster. Okay, so this is just fitting the maximum likelihood results over the, again, this is all things that Chris already did, so unless anyone has questions, I'll quickly move along it. And then just for comparison purposes, we are bringing in the, this is the default. And I'll discuss it in a bit more detail once we are actually looking at the mitigation measures. But this is essentially the default. This is the perturbative hybrid residual maximum likelihood. It's just essentially a method that incorporates or accounts for both low absolute and low effective sample size. So it's the best. It is slightly slower, especially if you have a lot of data, and can become quite slow. But it's the best one if you, especially if you don't are less concerned about computational cost here. And just to clarify here, the verbose equals true. The difference here is when you do CTMM.select with verbose equals true, it will output into this object all the different model fits that are being compared. If you don't do verbose equals true, which is essentially the default without having it equally false, essentially, it will only, the object will only be the best fit model. So just be aware sometimes if you're running it with verbose equals true, then you have for certain other things, then specify that you want the first object in that list, and that's the best fit. So that's why it has that. Does that make sense? Okay. Yeah, so if we check the summary of both of these. I think I started running the other one, but I don't need that if I already have the... Okay, so this would be the summary output from the maximum likelihood, and the summary output from the perturbative hybrid residual maximum likelihood. So it will show, you can see that there's some... Yeah, it's obviously not outputting the same exact values because, again, the way it's estimating the parameters is different. But in theory, if you have enough data, they should be close enough that you don't have too many issues. In this case, we do have effective sample sizes. So again, remember, it's this DOF, where you can check out the effective sample sizes. And for area, we have 20, which is still not like too great. I mean, if you're looking at hundreds or thousands, then these values would probably approximate more. In this case, they would still be different enough. So it indicates that probably for this one, you definitely want to stick with the default method, the PHREML. Okay, so now that we have the best fit model calculated, it's when we can actually do the home range estimation. Pretty simple with this AKDE function. You feed into it the data, and you feed into it the best fit model, right? Again, remember that's why this has the 1 here. It's because this is a list, and we want the best fit model here. Yeah.
Will always be the first one, the best fitting model that it gives out automatically.
That's
how it's built
in that list. Yes.
Okay.
But again, if you don't do verbose equals true, you don't need that square brackets one. Okay, so it should be fairly fast to run. Again, I'm running both of them in this case for, again, purely comparative purposes here. You don't need to do this every time. So this is just because we're interested in seeing the outputs. Okay, so if once you get the object out of the AKDE function, if you do the summary of that object, it's how you get the actual home range area estimate here, right? That's essentially how you get that output that you can report somewhere in the papers, in your thesis, whatever it is. And then we have this level.ud, the level utilization distribution, which is typically the 95% that's used in the literature. And for comparative purposes, if you're interested, it's the one that you would be using. And we can see here, there's just the difference between the maximum likelihood and the perturbative hybrid residual maximum likelihood. And that obviously we have slightly different estimates, though they overlap a little bit with the CI. So this is obviously the 95 CI for low estimates, the point estimate, and then the high 95. So as you can see, pretty simple. Just you can see like the difference compared to the maximum likelihood with the other one, and it's overestimating by about 5-6%. So the way to, if in this case for comparative purposes, but again the CTMM dot fit function can also be used to fit other types of model, not just the IID. But if you just feed in the data itself, in this case the pepper object, into the CTMM.fit, it will do the movement model that's independent. Like it would assume that there's independence and fit the model to that. That's what this is doing if you just put CTMM fit pepper. So in this case, it's going to essentially do the conventional KDE, right, without the autocorrelated information. And then afterwards, once it's finished running, we can actually plot them side by side. In this case, the extent function is just essentially grabbing both of the extents of the conventional KDE and the AKDEC. So when we plot them side by side, it's the same exact extension of values. Because if you don't do that, sometimes it will kind of fit to this one and fit to this one, and you'll see that the X and Y is not the same exactly. So in this case, it's fitting them, so the extent is the same. Okay, so as we've been seeing so far, the difference between the conventional kernel density estimator, the one that assumes independence, and the autocorrelated kernel, there's always this issue. Oh, did you decide? No, okay, there we go. Of not properly estimating the area and missing out on some of the areas that we know the animal might still use. So in this case, it's negatively biased compared to the AKDC, due to the autocorrelated nature of the data. Because again, we're forcing, for this one, forcing the data to be independent. Any questions so far?
I remember Chris was saying that the AKDE also has a tendency to underestimate a little bit.
Yeah, it's kind of like a scenario where sometimes, because there's multiple sources of bias, right? It's not just the autocorrelation that is a problem here. So there's biases that drive it to overestimate, and there's biases that drive it to underestimate. And sometimes the one of them is stronger than the other, and it kind of depends. And I'll show you in a little bit more detail, because we'll go over essentially the mitigation measures and how they work. But yeah, it is, sometimes it does one or the other, depending. Okay, so I'm just going to quickly jump back into the presentation. It should be it's just a few slides about the mitigation measures, just to give you guys an overview before we go into the actual code and see how these mitigation measures are applied. Yeah, as you can see, it's pretty simple to actually get the home range estimate out of it. Is it? Okay. It's just taking a while. My computer's slow right now. Yeah, it's just, I think that's the problem.
I'm just double checking this.
Yeah.
Because
Yeah.
some random errors in it.
Okay.
It's just
Sometimes
back
it
and
just.
back and stops automatically.
Okay, is it working?
Yes.
Okay, cool. Okay, so obviously there's some other biases that show up in the data, and we want to be able to account for them. And I'll go over at least the four main sources of bias that we can currently. Oh, sorry, yeah.
Yeah, we are writing KDEC or AKDEC. What is it correcting for?
I will explain that because that's one of the
Okay.
mitigation. That's why the C is there. Though that one is the default, as you'll know, I'll let you know. Okay, so this is organized kind of by the general importance. Though again, some of them, depending on the context and your data sets, maybe this one has more value than the autocorrelation. This is just in general, this is the order of biases, the magnitude of bias. Typically the autocorrelation, if we're not modeling the autocorrelation correctly, it's one of the main sources of bias that shows up in these data sets. Then there's sometimes the oversmoothing bias that I'll talk a bit in a second, the autocorrelation estimation bias, and this unrepresentative sampling in time bias. And all of them within CTMM, there's ways to essentially adjust for that. And this is where you see that I was talking about the perturbative hybrid residual maximum likelihood. It's one of them that will deal with the biases. But yeah, so there's always a way to kind of incorporate this a little bit and account for that. Okay, sorry, yeah. So the first one, again, you saw that sometimes I had added a C to the AKDEC. It's essentially one of the first mitigation measures that was applied into the AKDE. Essentially deals with this oversmoothing. So you saw sometimes that the home range estimates kind of go a bit, they spill out too much from the locations, right? So instead of, it's kind of that bias, right, that we always have, like how tightly conformed to the data must we be, right? So there's always some tendency for essentially any kernel density estimator that's based on the Gaussian reference function or related to that kind of tends to essentially oversmooth too much and go too far from the points. So it's essentially kind of a way to deal with that. This was with this area-corrected AKDE. And what it does is kind of like, so we have the density estimation, the location distribution estimation from a specific individual, and then it just basically corrects it a little bit without distorting the shape. So this is, this is a case where it would just be a circular, but any shape would count, and it just kind of conforms it more slightly to the data. It's just a slight correction for those events when it happens, because again, the method itself does tend to oversmooth. But this current one is the default. So you don't need to specify anything to run this area correction. It's already done as the default. It's just so you know that in the background, it's already doing that. So you don't need to worry about it spilling over a little bit because it's already accounting for that. So if it's doing that, it's because, again, of that same issue with the effective sample size, and the animal would eventually use that area. So it's the difference there, right? You don't need to worry about that. But basically, we can see that this bias, comparatively to the autocorrelation bias, basically one can mask the other a little bit, right? Because again, they're competing sources of a bias that are happening in the data. So in this case, we have the home range estimate with the correlated KDE and the conventional KDE for the same data that we've been looking into. And if we do the thinning of data again, we can see that they're approximating or being more approximate from one to the other. But this issue, essentially, if you start from large effective sample sizes where this would be very similar, right, between this correction and the actual autocorrelated KDE. So the error estimation is not too bad. It gets worse and worse with the lowering of your effective sample size. So at a certain point, you get overestimations that are significant for that area, right? In comparison with the correction and the not correction one. So the other source of bias is the autocorrelation estimation bias, which is all going towards, again, the same thing I was talking about earlier. How do we estimate these parameters, right, from the data? And using either maximum likelihood or residual maximum likelihood. And again, both of them have issues and either perform poorly at small sample sizes, both absolute and effective, or specifically at small effective sample size, which is the issue with these two that are commonly used even in other sorts of model selection. But Chris solved that problem for us as well. He developed specific estimators here that deal with either small effective sample size or small absolute sample size, or both together. And this is the one that I was talking about, right? The perturbative hybrid residual maximum likelihoods, which solves both of the issues of absolute and small effective sample sizes. But this one is the default now, right? So if you want to use the maximum likelihoods to maybe save some computational effort there, you have to specify that, because the PHREML will always be the default. And we can see here that this is data for the lowland tapir. So this is a tracking data set that was basically from 19 months of data. We just basically reduced it, truncated it to 2 days. This species has a home range crossing time of around a day. So they're very, very quickly cross their home range. So essentially, if we reduce it to 2 days, we have essentially 2 effective sample size, the number. And we can see here the difference. For example, the residual, I think this is wrong, ignore this. The residual maximum likelihood just overestimates this fully, right, comparatively to the other two, but then the maximum likelihood underestimates compared to the perturbative hybrid residual maximum likelihood. Again, for small effect sizes, this example is very extreme. It will be less defined if you have higher effective sample sizes. So this is just a very extreme example, so you can see the difference very clearly between the estimator methods. So for the final bias, which is unrepresentative sampling in time, the correction is the weighted AKDE or WAKDE. So obviously there's plenty of cases that can lead to irregularity. You can potentially do it on purpose with the duty cycling tags. Just basically you track during the day and you know the animal's not going to be active during the night, so it saves battery that way. If you have acceleration-informed sampling as well, but again, there's cases of device malfunction and there's gaps, or maybe even habitat-related signal loss, like a specific habitat that an animal goes into and you lose signal, and it creates gaps in the data. So there's plenty of causes for this irregular sampling. And again, you can shift the sampling schedule purpose for specific questions. But in any case, you can apply this correction, the weighted AKDE. And the general functioning of it is that it upweighs observations that occur under undersampling times and downweighs observations that occur during oversampling times. So it tries to kind of approximate a little bit. So it doesn't value too much if there's a time frame where the animal is tracked for every second, and then afterwards maybe it's for every minute. And it downweighs those second observations because, again, it's overly sampled. So we can see here an example. Again, we saw, if you remember, that DT plots for the pepper that had 1 hour sampling and then 2 hour sampling. So that shift and that malfunction is essentially this individual here. So we can see here, I'm just plotting where we had 1 hour sampling a difference in locations and the 2 hour sampling difference in locations. So this is with uniformly weighted AKDE. the home range, both the 95% contour and the 50% contour. And then we can compare with the optimally weighted one. So we can see that, if you remember, these were essentially the oversample times, closer in time comparatively to the red. So it's conforming more to this side and giving less importance here and slightly more importance here because, again, there's the shift. And you can also see that it's also kind of in space because that's where it happened most. So it adjusts the AKDE output a little bit to account for that. Yeah.
So when we plotted, we have this 1 hour and 2 hour, but there was also other information from like longer periods that when it loses signal or something.
Yeah.
So how are you just took those away, or are those still represented within?
They're still
this?
represented there. They're all in there. We're not subsetting the data in any way. We're accounting for the information that's already there.
Okay.
There's no removal of points.
Okay,
yeah.
So are those points considered within the red ones that are every 2 hours, or like visually here?
You mean when I plotted the difference, right? Yeah, there's obviously some points that are not exactly 1 hour and 2 hours apart. It's just a quick visualization.
Okay.
Yeah.
Yeah, I was just wondering because.
Yeah.
Quick question. When we want to calculate the core area, is it also common to use always 50%? Or
the literature, the way everyone does it is with the 50%. Yes.
Okay. Thank you.
Okay, there's a final one which is related to very low effective sample sizes. So it's a correction that you only really apply if you're in that case of the Mongolian gazelle, right, of the 1 or 2 effective sample size, or maybe below 5 is usually the cutoff here. And it's going a bit beyond this perturbative hybrids residual maximal likelihood correction and going into parametric bootstrapping. It's essentially we try to approximate the sampling distribution to the true fit, to the true best model. But yeah, so the idea with bootstrapping is pretty simple. You're just sampling from the data. Just sampling from the data, and obviously you have your sampling distribution, but you can keep doing that and resampling over and over again until you actually get a bootstrapping sampling distribution that approximates the true distribution a little bit better. But it's, as you can imagine, if we're constantly resampling from the data to get different estimates, this can take a long, long time. So any bootstrapping process is very computationally intensive. But it is, if you're trying to just squeeze a little bit out of data that's very low effective sample sizes, it might be a way to go. Yeah, and I'll show how to do that as well. So this is just a comparison between all these different corrections, also comparatively to the conventional kernel density estimator. This is on the x-axis the sampling duration, and then we have the relative error of the home range estimation, right? This is all based on simulations, by the way. But essentially what we see here, and the way I set up the simulations was for the home range crossing time to be 1 day, right? So this is essentially the same as the effective sample size. If you remember dividing the duration with the home range crossing time. So it's the same information there. So we can see here for both the conventional KDE, which is the yellow, again, you need very large sampling duration and effective sample sizes for it to get close to 0 relative error, right? And then it starts getting better with some of the corrections that we have, both the area correction and then this PHRML as well. And then we have the bootstrapping, which is this one here, which helps us correct even more for these cases for low effective sample sizes. But again, you saw that I didn't even run it beyond this, because again, there's also no points. But it's also very computationally intensive to run. But it does help reduce the error even for very low effective sample sizes. But as we can see here, the 1 and 2 area, it's still you can get like 50% errors to 25 errors. So it's still relatively big. So you have to weigh if it's actually useful at that point to actually have a home range estimate. But hopefully none of you have the issue of that low of effective sample size. But yeah, so this is just plotting the computational cost. This is log transform, by the way. But yeah, you can see it just goes, yeah, it takes a long time to run, especially if you have a lot of locations. So it can take hours. I've heard some people that it takes some days for them. So yeah, it can be a problem. Okay, so let's go back to the script. And I can show you how to apply these measurements. Though, does anyone have any questions at this point? No. It just doesn't like to change screens. Okay. Okay, it's working?
Yes.
Okay. Okay, so the first thing we're going to look into is to fix this irregularity representation in time with the weighted AKDEs. So we're going to go back to this individual paper that had that malfunction. Again, if you just want to quickly get the sample sizes out, you can just use this. If you do summary of the fit object, and then $DOF area, you just get the effective sample size output directly here. So that's 15. And then if you want the absolute sample size, just for comparison purposes, you can just count the number of rows that are in the data set. Okay, so this is the same plot I was showing earlier with the 1 hour to the 2 hour shift. And just to show, because sometimes it can be hard to see what the value is, you can draw a line. In this case, I drew the line at 2 hours with this abline function, and it just creates that line at the 2 hours. Yeah?
What are the dots on the right?
So these are, you mean these ones and these ones here, right? It's because obviously not every single location is exactly 1 hour apart, and not every location, even when there's a shift, it's 2 hours apart. There's a few other gaps in there that mean that there's different sampling intervals throughout the data, right? So sometimes you get a data set that's very regular and you don't have any issues, but there's always some locations that are far apart. Maybe that was a day where it didn't collect a location, so that's what explains like this one's over here, right, and some other gaps. Yeah. Yeah, because this is just a diagnostic tool, and you can see that the vast majority of points are one or the other, right? So it's not as dramatic of a shift. I mean, if you do the DT plot of one of the buffaloes, that shouldn't have that issue. So you can see it looks better, right, comparatively. It doesn't have that big shift. So you can be pretty sure that in this case, you don't need to apply the WKD correction. Yeah, there's always going to be a few cases that pop off. Okay, so this next part is just showing you how to plot the two colors. Oh yeah, sorry.
It's kind of the same question, but it was trying to understand like
Yeah.
When we would need to use the weighted, like how much variation can we accept before we should be using
I mean,
the weighted?
This is a diagnostic tool. Obviously, you can use it to kind of make that decision.
Yeah.
If you already know from your data that, for example, you set it up in a way that you have gaps, then it's better to apply the mitigation measure because it will always help correct
What if
that.
there's just like error in the tag?
Well, if there's an occasional gap here and there, it's not necessary, right? If it kind of looks like this, even if it has a little bit extreme values in one side or the other, then it's an acceptable level of gaps. Because the AKDE can still account for that a little bit. It's just, this is a correction, right?
And then just another question.
Yeah.
If we're running like all of our individuals like in a loop, should we
Yeah.
be using like weighted AKD automatically if some of them have irregularity in their sampling frequencies?
If some of them have it, then it's better to use it. But you can also, again, first do this evaluation and just apply it for the ones that have that big of a problem, especially if you have a loop of, a lot of individuals, because this correction also adds computational time. So it's something to consider when you're doing that.
Sorry, I think it's a quick question, but the x-axis on here is not the order of the points in the track. It's just sorted in terms of the time interval?
Yeah, it's sorted in terms of the timing, yeah.
Okay, that makes
Yeah.
more sense. Mark, did you have a...
No, my question was answered.
Okay. Okay, so this is just to show you how you could do that plot of the different colors for the different times. Maybe it's useful for also the diagnostic tool. The main difference here, if you're doing for your own stuff, is to set what is the threshold that you want to change the colors on. So I put 1.5 hours. So yeah, that's what when we're showing the plot, it's including more than the 1 hour and the 2 hours, obviously, when we're just doing anything that's below 1.5 and anything that's above 1.5. Okay, so to apply the correction is pretty simple. Again, this is the same logic as before with the AKDE function. You feed it the object of the data. You feed it the movement model. In this case, remember, this is still the verbose equals true, so it has a list, and we want the first one. And then the only thing that you need to do extra from that is weights equals true, and that's it. And then you do the correction. Yeah, in this case, it's not too slow. At least when I ran it on my computer, it was 2 minutes, so it's not too bad in most cases. So I guess you can, if you have issues with your individuals and having irregularity of sampling, and it's not taking too long, it's always better to apply it if you have irregularity. Yep.
If with some individuals you have a really big sample size, but with others quite not so much, will you then use different methods, different AKDE, or?
Like you mean comparing within AKDE to do different things, or with different methods outside of AKDE? Because that's a
no,
problem.
within AKDE, like, yes, if you have a few individuals that have really low sample size, but the others you have a big sample size.
The idea with AKDE is that it's comparable across individuals anyway, right? It's doing in such a way that it is comparable, even in those cases. But obviously, if you have a very, very low effective sample size individual, and you're trying to do the home range estimates, maybe remove that from the evaluation. But at that point, maybe that one already doesn't fit the range residency assumption anyway.
Yeah.
Yeah, so that's kind of, maybe in that case, it's more about selecting the individuals that do fit the assumption and then just run it with those ones.
But then it's not possible to compare individuals.
It is possible to compare individuals.
Okay.
Yes.
Okay,
Yeah.
okay.
The estimates at this point, you can compare them. Yeah.
Okay.
Can you?
I think in some contexts, if you have some individuals that are range resident, but you just don't have very much data on them, it can make sense to bootstrap those individuals and just do the regular non-bootstrap for the rest of the individuals. I think that makes perfect sense.
Okay, so this is once again just plotting them all side by side, just for comparison purposes, just so we can see. But it's very similar to the plot I was showing in the presentation. But yeah, the difference between the weighted AKDE and the unweighted AKDE. Obviously, if you don't have regularity of sampling and you apply this measure, it'll be fine. You're not ruining the estimate in any way. It just obviously would take longer to run. But yeah, so it's obviously in this case that we have irregularity. You can see the difference more clearly. Yeah, and the value is slightly different. I think I was using a different individual. But yeah, so the difference between, in terms of just area output, is not very large. Yeah, less than 1% in this case. Okay, so for the low effective sample sizes, so this is just kind of a, so you have some idea of when you should apply the different methods depending on your effective sample size. For maximum likelihoods, typically you would want a DOF of more than 20. For the perturbative hybrid residual maximum likelihood, you want the DOF definitely above 4 or 5. And then if you have very low effective sample size, that's when you need the CTMM boot, which is the one that's going to do the bootstrapping. Yeah. So just a quick guideline of when you should apply the different methods. So within CTMM, there's also the date of the Mongolian gazelles I was showing earlier. So we can see how to apply the bootstrapping with those, because those ones are the ones that have the very low effective sample sizes. As we can already see, we have very few locations already, even just looking at the number of locations here on the plots. Yeah, so it's the same process of obviously going through the CTMM guess and the CTMM select, getting the fit. It should already be running in that object that we loaded earlier. And we can see here the effective sample size for this particular individual is 4.5. So it's not the most extreme of the gazelles, but it's still relatively low. So this is where we make essentially the decision: do we need to bootstrap or not? Once again, just to quickly either roughly calculate the effective sample size or to get it from the movement fit. That's what these lines of code are doing there. So first, just for comparisons with afterwards, we're just going to run a regular AKDE without the bootstrapping. So that will be this information here. And this is the expected order of bias from the perturbative hybrid residual maximum likelihood. So expect around 5%. So maybe we want lower than that, right? We want to, in this case, an error target of around 1%. And that's where the CTMM function, CTMM.boot function, comes in. So this is essentially going to replace the movement fit into the AKDE function when we calculate it. So you have to run this before. So it's the same logic of fitting it the data and the object. And you can also set that this can be, there's a default anyway, just if you want to change it, you can set a different error target. The trace just means that while it's running, it will give you some updates and information of, so it's helpful just to know it's running and not stuck somewhere, because sometimes with R it gets stuck and you at least know that something is going on. And this argument here is if you want to do parallelization and multiple cores, but I don't think it works very well on Windows anyway. But yeah, so in case you have a different system and you want to speed it up a little bit so it's faster. So in this case, as we see here, on my computer it took 40 minutes for this to run. So obviously we're not going to do it now and wait until 40 minutes from now. But it's already run for you guys, so it should be available in the outputs, and we can just see what it looks like. But yeah, so it's a big difference from what we had before of a few minutes to 40 minutes, right? Yeah. Question? Yeah.
Just to go back to the approximate effective sample size.
Oh, yeah.
I noticed that the value, the 5.88 value that you used is not the same.
I might have changed individuals, and that's why it's not the...
No, but if you go to the summary, I thought we were taking the position estimate, but this is the higher interval.
Yeah,
Is there a
I
reason
just
for that?
copied the wrong one.
Oh, okay.
Yeah, that's just me doing it wrong. Now, in this case, if you're doing the ref, it should be the estimate, right?
Okay.
So it would be this one here, yeah. So yeah, you're correct. Okay, so this is the output from the boot function. It's essentially, again, replacing that movement model fit that we're going to use. And you can see here just the expected order of bias from this one. It's close to the error target that we set up. So it's pretty good. So to run the actual AKDE with that bootstrapping information, you do instead, again, remember we're doing the fit here, but now we do the boot object, right? And in this case as well, we could do weight equals true if that's, because again, we can combine these different mitigation measures. If you have multiple sources of bias, you can do multiple ones, and that's why the weights equals true there as well. Yeah. So you do that, and then you get the estimate from that bootstrapping. So you can see that it's obviously giving you different estimates, outputs from the non-bootstrapping and the bootstrapping. But this one, obviously, in this case, is the one you want to use because it reduces some of that bias. And just to quickly, again, plot them side by side. It's not going to look too much different, at least not easily perceived in these plots, but there's some slight differences there. Maybe if I plot one and then the other is better. Okay, so this is without bootstrapping. It should change to the bootstrapping one in a second. So yeah, the difference is, yeah, a little bit, but not super noticeable, but it's still giving you a better estimate. So obviously, bootstrapping is definitely not default. The weighted AKDE is also not default. The pH REML is default, and the area correction that is applying on top of everything is also default. So you don't have to worry about those two. But with the representative sampling in time and with low effective sample sizes, you have to be aware of it and change things if you have to. Okay. Any questions at this point about home range estimation? Okay. So if you're not too tired yet and don't need a break, we can move on to population level inferences. Yep. Okay, so before we get into the script, I'll just go over some slides explaining this a little bit. But the main idea here is that when we're trying to look at population level inferences from this home range estimation, we want to be able to account for the uncertainty that's being generated. And if you just take the home range estimates and you just do the mean of all the point estimates, that's not really accounting for that uncertainty, right? So within CTMM, there are ways to do that in a more reliable way. So basically, if you're trying to estimate area requirements that goes from the individual level to the population level, or maybe you want to quantify the effects of covariates, different species, like compare different species, different sexes, body size, age, movement characteristics, habitat, a bunch of different covariates you can look into. And also, especially, if we're comparing different populations with different movement behaviors or sampling schedules, we want to make sure that we're doing a method that can make that comparable and easy to get an output from. So typically for population level inferences, there's a lot of non-hierarchical models where basically we get information from the observations that inform one parameter, right? And that's basically, it's pulling all the information from all the data into that one parameter. But if we want to compare different groups, right, we have different parameters that we want to look into, maybe different sexes, maybe different habitats or something like that. And if we're trying to use these non-hierarchical models, basically we're assuming that they're independent from one another. There's no sharing of information there, right? No pooling or sharing of information. The trick then is instead of using these non-hierarchical models, use the hierarchical models. Right, and the difference here is because, again, we want that information from the different groups, but we know that those different groups are not independent from each other. So essentially, we have the observations, the data points that are informing these factor level parameters, and the factor level parameters are governed by this additional parameter, that's a population parameter. So the structure is needed if we don't want to lose that information from one step to the other. So with the animal movement data, you start with the data, you account for that, you get the information from the actual trajectories and the probability distributions there, the individual home range estimates, and then you get to the population level inferences here. So if you have all the different home range estimations from all the different individuals, which are represented here with different colors, right? Then we can propagate the uncertainty that is from each of those home range estimates into a mean value that accounts for that, instead of just getting the point estimates and doing a mean directly. So this is just an example with lowland tapirs again. If you remember, I showed it earlier. They have a home range crossing time of less than a day, so very quickly they cross their home range. So they're a good case study to look at the effects of essentially subsampling and seeing how different truncated data sets have on this mean home range area, right? The pooling of data and the propagation of uncertainty. And this is comparing the sampling mean, so just getting the point estimates and getting the mean directly, or using our method, which would do this hierarchical modeling, right? So we can see that if you just do the mean of the home range estimates, you're always going to underestimate the home range area comparatively if you're subsetting by shorter and shorter time tracking durations. And it's the same thing with individuals. Like, it doesn't matter how many individuals you have, your mean is not going to approximate the truth if you just do it directly like that. But our estimator, even with very low number of individuals, gives a good mean home range area. The good thing about this method as well, you only really need 2 or 3 observed home range crossings and a similar small number of individuals. So even if you have only 2 or 3 individuals, you can still use this method to get the mean home range area for all the individuals. So that's good. Okay, so there should be a script called 3meta, I think, if I remember correctly. Let's see. Yeah, CTMM_3_meta.
What was the name of the script?
This, sorry?
The name of the script?
CTMM_3_meta.
Ah.
Yeah. Okay, so everyone has a script? Okay. So once again, I pre-ran some things in this object. So just make sure you load that in case things start taking a long time. I guess the main difference here, because before we were kind of looking at one individual at a time. So obviously here we're doing a meta-analysis of multiple individuals. We want to have all the model fits for all the individuals. And in this case, the way it's set up here is just doing a for loop and doing one individual at a time. Everyone here familiar with for loops? Okay. Okay, yeah. So it's just running one and then the other and then the other and then the other until it finishes all of them. But this should be available to you guys already if you load the meta object. Yeah, so this object here now, the fit list, has all the best fits for each buffalo. That's all that's doing. As you can see here, instead of feeding just one data set and one fit, we're feeding the whole, this is the list of all the buffaloes, and this is a list of all the model fits for all the buffaloes. So it's doing it to one function. You don't need to do a loop in this case. You can just run all here. So the object would be essentially a list of all the AKDEs for each buffalo. But it's already run as well. And just to plot it real quick so it shows, yep.
How do we include the mitigation stuff?
If you're trying to do it here, so if you have the AKDE, like the weighted corrected, you could do the weights as well. Equal true or something like that. Like, true, right? So you're adding the mitigation measure for the weights. In this case, the CTMM select, it's doing the PHREML already as the default. So unless you want to change it for the maximum likelihood to speed it up or something like that, which you would add to this part, right? If you wanted to do a different method, you would change it there. And for the bootstrapping, you'd have to do the CTMM boot here and basically go through all of those, right? So that would be how you change this to account for those. Okay, so it's just plotting all the AKDEs, different colors. And just so for comparisons, we're just doing it the old way of getting all the point estimates, right? So just from the summary itself, we're getting the point estimate of the home range and just doing a mean directly on that. So this would be the old way of doing it. And you have this output of 458 square kilometers. Now, if you don't want to do it the old way and you want to use the way that accounts for and propagates uncertainty, you would use this meta function. You're feeding it the AKDE list. So this is the list with all the different individuals. The main difference here is that we can also get some extra outputs. Just gives you more information with the CIs and all of that. This is just saying, so it plots all of them with different colors, but then the mean is in black, and then it sorts them, so it's by largest home range to lower home, like smaller home range. Yeah. So you can see here the point estimate and CIs for each individual, and the point estimates and the CIs for the mean home range. One thing this also tells you, as you can see here, it's comparing the direct delta and the inverse Gaussian. The inverse Gaussian is the one that essentially accounts for variation. The direct delta just says there's a point estimate and there's only one point. It's a specific distribution that's just one value, right? Instead of being a distribution of values. So this is basically saying that it's that's the one that has lower AICC. So it's the one that's being selected there. So basically it means that there's not enough variation in the data. And this mean is pretty, like all individuals are around the mean, right? So the mean is the best model there. And you can also obviously get with the information here, the mean with the CIs, if you want to report that. If you want to compare different groups, in this case, it's kind of arbitrary and it's not necessarily very biologically meaningful, but the way you would do it is just create a list with the individuals that you're interested, the two different groups, right? So it could be males versus females, and you just select the AKDEs for the males and the AKDE for the females, and you create a list that separates them, and you can actually compare the different groups. Okay, so that's showing the individuals in the south and individuals in the north, and the mean of the two groups here. But we can see from the outputs that they're not different from each other. They're still, the variation is not meaningful here. Right, because if there was evidence of a subpopulation, typically the AIC of the subpopulation model would obviously be lower. But in this case, the joint population model is pretty much, it's close enough that, again, there's no difference between groups in this case. This separation between south and north when trying to look at home range estimates is not showing any pattern there. But yeah, it gives you, again, the estimates for each of the groups, and even the ratio comparatively. So the north is for the low and the point estimate and the high. So that's what that means. So if you're looking at the point estimate of the ratios, it would be this. So the north is 1.3 times the south. That's how you'd interpret that. And then obviously if it's 1, it means they're the same. But it overlaps with 1, so again, there's no difference between these groups. So if you're trying to do it with your own groups, you just have to change that particular list, whatever you're interested in.
So these comparisons are just always ratios are just...
Sorry,
Sorry, these comparisons are just odds ratio and just it, or what?
Sorry, I couldn't understand.
What this comparison stands for? This between the north and the south. It means that they are these are indeed odds ratio comparisons.
The ratio?
Yeah. Yeah,
Sorry,
between the north and the south. Sorry. I mean, whether this comparison between the north and the south, you mean that it was a 1.3 higher the.
Yeah.
So you mean whether these are computed as odds ratios in weighting the function, or
I don't think
calculated?
So.
Yeah.
I don't think so. I think it's just an actual ratio. It's not odds.
Okay.
Yeah, yeah.
It's the ratio of the mean.
Oh yeah, yeah, that's the point. Yeah. Okay.
Okay.
Okay. Thank you.
Okay, any questions? It seems pretty straightforward at this point, so I'm sure, and then if you try to do your own stuff, then it's when problems start showing up. Okay. So Chris is going to cover just very quickly the population density parts, which is other population level things you can do within CTMM. If Chris is ready.
So on the GitHub, I will be working at the end of the CTMM AKDE script. And this won't take very long. So I'm talking about and load the environment, load the data, project the data. Let's see, I'm gonna go down here. Yes?
Have you changed anything from the code from yesterday? Like, we don't load everything?
And this, no, no. Let me go down here. And load these fits here, and the AKDEs from basically the same material that Inês just covered. And then get to the last section on population density estimation. So I have some slides. Okay. So if you've tracked a bunch of individuals, and these individuals are representative of the population, and you want to know the population range, then typically people would take all the home range estimate polygons, which correspond to coverage areas, and if these are the 95% MCPs, they'd merge these polygons and they'd say, this is my 95% population range. So this is on simulations. We've done the same thing on a few species, and it comes out the same. So these are KDEs, and these are AKDEs, a little bit bigger. And this is still bad. So these are merged polygons again. And here I'm doing something different, but still bad, for estimating the population ranges, which is instead of merging the coverage areas, which statistically actually doesn't make any sense. Statistically, merging coverage areas of different components of a mixture doesn't give you the coverage area of the mixture. Like that just, there's no math that says you can do that. Here, what I'm doing is I'm taking the distributions and I'm averaging the distributions. That makes sense if these individuals are all the individuals in the population. So there's two functions in CTMM for averaging distributions. One is the mean function, and that's what you use when the things you're averaging are everything. There are cases where you would do that. For instance, you have an individual where it has a summer range and a winter range, and you want some sort of combined annual range. Well, there's summer and there's winter, and there's no other seasons that I know of where there's not super summer or something, right? So that would be everything. But if these are just a few individuals from a much larger population, then the problem with this is that there's a bunch of untracked individuals. And if you included more of them, you'd get a larger population distribution estimate. So both of these methods, merging the polygons or averaging the distributions, they're both going to underestimate the population range because they're missing some model of the variance of the individuals that would help predict the additional space use of the untracked individuals. So we have another more complicated method. This is going to be submitted pretty soon, which is the population kernel density estimate. So in the autocorrelated kernel density estimate, you're optimizing the bandwidth for one individual given that the data is autocorrelated. Here, you're going to put the kernels down on every point of every individual, and when you optimize the bandwidth, you have to account for the fact that you have a bunch of individuals, they're autocorrelated in their own data, and their distributions are not the whole distribution. So there's the autocorrelation problem, and there's the hierarchical model problem. And so the math is just slightly more complicated for the population kernel density estimate than for the regular AKDE. But what you get when you look at the saturation curves, so traditionally people would do one of these two things, and then they'd make saturation curves as they sample more individuals. How does their population range estimate increase? And they would ask, how many individuals do I need to track to really know what's the range of this colony or something? That's the question that they want to ask. And even averaging, taking the mean of the AKDs, it's going to take a while to saturate. And it's going to be negatively biased. All these methods are going to be negatively biased, again, because they're missing any accounting for the untracked individuals in any of these methods. So here, with the population kernel density estimate, there's no minimum number of individuals you need to track. It's just that the fewer individuals you track, the bigger the uncertainty is you get out for the population range. So it's just what amount of uncertainty are you willing to live with? And back to the script. So there's its own function. There are a few options, nothing really to play with yet that you need to. You have to run, you go through the same process. You get your models, your autocorrelation models. You have to get your individual AKDEs. And then once you have those two lists, it's going to do a bunch of stuff. The first thing it's going to do is figure out from the individual models, what's the hierarchical model for all the individuals. And that shouldn't take too long. And it has to do some model selection there because there are all these different parameters, and you consider all the possible correlations between those parameters in the population. That's usually too many parameters. So you got to throw some away, and model selection is a good way to do that. And then after that's run, which that had already finished once it got to that last line, then it's optimizing the bandwidth for the whole population, or I should say for the whole sample of all the individuals, which takes a little bit longer than adding up all the computational times for optimizing each individual's bandwidth. So however long it took you to run every AKDE, expect this function to take a little bit longer than the sum of all those times. But it is like linear. It's not, you double your data, it doubles the calculation time, that's ideal. But it takes a little while. No, I didn't run the color. What was that? There we go. Yeah, so you get something in this case, because you only have 6 tracked individuals, your population estimate is quite a bit larger than what you'll get if you just do them straight mean, which I skipped over. Sorry. So this is the straight mean of the distributions. And it's literally the mean of the different distributions. So each of these AKDEs all averaged together, that's all it's going to be. So it's generally not going to be that big as compared to the population kernel density estimate, which is extrapolating from the sample of tracked individuals to some larger population of individuals that are mostly untracked. So it's just one extra line. Yeah, I've got a question.
Yeah, you can kind of see it here. I'm just wondering if it matters that your individuals might also be correlated in terms of like social interactions.
There is one pair that half of the time is correlated. A lot of them look like they are, and they're not even being sampled at the same time. It's just they like the same places. Yeah, so that is not, I think, like I said before, we don't have correlated movement models in place yet, because most correlated movements that you guys actually go out and track are not like 100% all the time. They're on and off. And you have to have a behavioral switching model in place before you should be doing that. So we'll have that in, and in this case, it would make a slight change in that the data on the 2 animals, the 2 buffalo, when they're moving together, that would be even less independent than you thought. So you'd have even less data than you would consider. Yeah, so that is an issue with if you have a bunch of tracked individuals and they're in a herd. This method at present would assume they're all moving independently, and so the uncertainties would be very much underestimated.
So
Yes.
I know that is not the case for these buffaloes, but for example, if we have individuals sampled from 2 different populations running everything together, we'll assume that it's just one continuous population and it will create something like this,
Yes.
right?
Yeah.
But in that sense, you should be able to very distinguish with another factor. This subset of my data set is this population and this one.
Yeah, so if you have 2 populations, you would probably want to run it twice with PKDE, population kernel density estimation. And then if those are the only 2 populations, then you would mean them together. And that would be the, I don't know, geographic range or something, whatever it is.
You said that we can use this mean function on an individual, like if they have 2 separate
Yeah.
ranges. If it's probably very specific to my data, but if you have individuals that are commuting between different areas, maybe daily or weekly, but it's not necessarily divided by season, could you use that for that?
Yeah, you could. If they have like multiple homes, then you could mean those together, and the assumption there would be these are all the homes. These are all the home ranges.
And can you then incorporate that individual into this PKDE?
It's a good question.
Because you're like meaning it and then meaning it.
Yeah, I think that would screw everything up in the way I have it coded, because you'd have two movement models. No, I don't think the way I have it coded, I don't think that would work yet.
Okay.
You could.
But if it's just one individual, would it matter if I left that one out? If it's
Yeah, you could do. Yeah, I'm not sure if there's anything the way I have it coded, I didn't think of that.
okay.
Sorry. Gotta.
I was just wondering what the weights argument in the PKDE function accounts for then, if it's not the individuals themselves.
It is an idea I had, which was maybe I should weight some individuals more than others, in the same way that the weights on time work. If you sample irregularly, then optimizing the weights on the times helps a lot. But I did that, and I tested it, and I didn't like how it works. So I don't recommend. We haven't published this yet. We've done a lot of testing, and there's that argument there, and there's another argument. What am I doing? I do need help. Kernel equals individual. There's another argument. You can change that to another thing, but we tested that and didn't seem to be useful at all. I really didn't like per individual weights, because if two individuals were kind of near each other, it would just turn one of them off. I was like, I don't like that. That doesn't feel right. So I didn't think that was helping any. And that's it. It didn't take that long. So now it's Inesh's turn again.